In this video, we're going to cover sections 1.6 on electronegativity and bond polarity, as well as section 1.7 on dipole moments and molecular polarity. Electronegativity is thought to be one of the more important concepts in organic chemistry. Some would argue it's the most important concept that one should know when learning organic chem. And I tend to agree because electronegativity allows you to look at an organic structure and identify regions within that molecule that contain polar covalent bonds. Polar covalent bonds are where reactions occur from. And so it's important to be able to identify where the possible reactions can occur in a structure based on identifying the presence of these polar covalent bonds. But to do that, you have to recognize that there is a difference in electronegativity between the elements. And so one definition that we can use to describe electronegativity is what's shown here, is that it's the ability of an atom to attract electrons it is sharing with another. And as a result of that unequal sharing of electrons between one atom and another, we polarize the bond. So we generate some polarity. There's going to be one atom in which will attract the electron density more often than the other. And so we will think of this unequal sharing of electron density between two atoms as a polarization of the bond between those two atoms. So the greater the electronegativity of an atom, the better it's able to attract electron density around its nucleus compared to that of its neighboring atom. So in a periodic trend that is typical, we often will say that the electronegativity is going to increase from left to right and from bottom to top. And so we'll say that oxygen is more electronegative than nitrogen, which is also more electronegative than carbon. And similarly, when we look at the halogens, we'll say that bromine is less electronegative than chlorine, and the most electronegative element being that of fluorine. So when we look at organic structures, as I was mentioning, for example, if we take the carbonyl is a part of a greater organic structure. It's found in ketones and aldehydes, found in carboxylic acids and carboxylic acid derivatives. When we look at the nature of this double bond associated with the carbonyl, the carbon double bond oxygen, we know from our previous lecture that this is composed of a sigma and pi bond, and that there's 4 electrons associated with the bonding between these two elements. But we can say, based on electronegativity arguments, that the electron density is going to spend more of its time around oxygen and less of its time around carbon. In doing so, that double bond we say is polarized, that there's greater electron density found around oxygen than found around carbon. And so we can use these symbols, these delta minus and delta plus, to represent that there is a little more electron density in one region of the overall bonding system. So there's more electron density found around oxygen than carbon. And so therefore, we have a polar covalent bond. And that becomes important when it comes to identifying sites of reactivity. So there really are two extremes to bonding. We have covalent bonds, which makes up the majority of what we'll discuss in this course, as well as ionic bonds, which are generally found in our salts and some of our reagents that we'll discuss later on. So the difference between the two has to do with the extremes with respect to electronegativity differences between the elements that are bound to one another in these particular structures or bonds. So a covalent bond is a type of bond that results when the atoms have generally the same or similar electronegativities. So we think of that as our H2, CH4. These are all systems that the electronegativity differences between atoms of similar electronegativity are going to result in a fairly equal sharing of electron density between those elements. For diatomics like H2 and Cl2, because electronegativities are identical for each of those atoms, hydrogens or chlorines in those two examples, they're going to be really apolar or nonpolar systems. An ionic bond, on the other hand, is when you have really the attraction of two oppositely charged ions. So typically NaCl, where really in aqueous solution, we have dissociation of this ionic bond into sodium and chloride ions. And even in the solid form, it's an intricate network structure of sodium and chlorine atoms, but we don't consider the bonding between these elements as being covalent. They're ionic, and partly due to this concept of electronegativity, that their electronegativities are extremely different. Now, the majority of our course, we're going to be looking at polar covalent bonds. As I've said, this is where reactivity occurs in organic compounds. And so a polar covalent bond is a type of bond that results when atoms of different electronegativities share electrons. So that could be, as in our previous example, between carbon and oxygen, carbon and nitrogen, nitrogen and oxygen, and even more clearly between the halogens and carbon. And this makes up a family of compounds that we'll discuss soon, which is the alkyl halides. Now, bonding electrons, these are attracted more strongly by one atom than by the other. And so again, because bromine and chlorine are more electronegative than carbon, we will often show those types of structures. So if we look at a typical alkyl bromide, we think of the electron density spending more of its time around the bromine atom. And as a result, we think of this polar covalent bond as having a dipole associated with it. We have bond polarity. We have polarization due to the differences in electronegativity between the bonding elements or atoms. So it's key to remember that electron distribution is not symmetrical, that in polar covalent bonds, one atom is going to have, in a sense, an unequal share of the electron density that's being shared between those two electrons. So more electron density will be found around the atom of higher electronegativity as opposed to one with less. So when we look at a typical structure in organic chem, in this example, we see we have an alcohol, methanol. Again, this idea of electronegativity allows us to focus in on where we expect to see differences. And so we see oxygen, we see a hydrogen and a carbon. This is going to be something that we'll see quite readily, that there's obvious differences in electronegativity between those elements. So we should expect to have covalent bonds, but more importantly, polar covalent bonds associated in that region. And so in this question, to identify all the polar covalent bonds in the structure, you're going to be looking for bonds between elements that have differences in electronegativity. So as you can see, we would identify as, both the oxygen-hydrogen covalent bond as being polar, as well as the carbon and oxygen bond as being polar. And in both instances, the oxygen is more electronegative than both carbon and hydrogen. And so therefore, when we're drawing our bond moments, and we use this particular symbol to represent that, the arrowhead is going to point towards the more electronegative element and the tail towards the less electronegative atom. And so we can also indicate the partial positive and partial negative charges associated with the elements in these polar covalent bonds. Oxygen, in this case, being the most electronegative element of the three, will carry the partial negative charge, and the delta positive or partial positive charge will be associated with the hydrogen on one side, on the right side, and carbon on the left. So section 1.6 leads us into 1.7 quite nicely. Then now we can think about not only bond polarities associated with polar covalent bonds, but how multiple bonds of different polarity can give rise to a molecular dipole moment, or what we refer to as molecular polarity. So when we talk about dipole moment, what we need to do is consider the various bond moments associated with the bonds within a particular molecule. So for example, in chloromethane, this is said to exhibit or have a dipole moment because the center of negative charge and the center of positive charge are separated by one another by a particular distance. To simplify that, again, we can just look at the nature of the electronegativity between the chlorine atom and the carbon atom. And we know there's a substantial difference in the electronegativities of those two atoms based on our periodic trends. And so as shown, we can draw a bond moment associated with that. We can show the polarity. We can show that in general, the electron density is going to spend more of its time around the chlorine atom than that of the carbon atom. And if we take a step back and look at the rest of the molecule, we see that we have 3 carbon-hydrogen bonds. But again, the differences in electronegativity between carbon and hydrogen are relatively small, and so we don't consider these to be polar covalent bonds. So from the molecular standpoint, the polarity of the molecule really is heavily dependent upon the difference in electronegativity between the carbon and the chlorine atom. So we say that this molecule has a dipole moment, and as a result, it has polarity associated with it. So when a compound has more than one polar covalent bond, what we need to do is we need to take, in a sense, the sum of the two, the vector sum of the two. And again, we're not going to be doing any vector calculus to describe this, but if we look at this example, you can see that in this molecule, dichloromethane, we have 2 carbon-chlorine bonds to chlorine from the same carbon atom. And so again, similar to what we did in earlier examples, we know there's going to be a partial negative charge associated with the chlorines because they have a greater electronegativity than the carbon, and a partial positive charge associated with that carbon center. We have it's a tetrahedral molecule, and we have two dipoles that we need to consider when determining the overall dipole moment of the molecule. So the vector sum is called the molecular dipole moment because it takes into account both the magnitude and the direction of each of the individual dipole moments. So we have a dipole moment pulling in this direction, as well as one in this direction, and the resultant is going to lie somewhere in between, as shown. Lone pairs on molecules like ammonia and water, these two can contribute to the net dipole moment. And so we see in this example ammonia that, yes, we have individual bond moments associated with the NH bonds, but we also have a significant bond moment, well, not only a bond moment, but a moment, dipole moment associated with the nitrogen center and the lone pair, which is found in an sp3 hybridized orbital of nitrogen. Similarly, for water, we have individual moments associated with the differences in electronegativity between oxygen and hydrogen, but we also have bond moments or moments between the oxygen center and electrons within an orbital, an sp3 hybridized orbital on oxygen. So these two contribute to the molecular dipole moment of the molecule. And so as you can see, it has a fairly significant effect on the overall molecular dipole moment in such that the dipole moments are shown. So we have a dipole moment that is pretty much in the direction of that lone pair, and for water, in the direction that is equidistant between those two individual moments associated with those lone pairs. So again, ammonia and water, these would be considered polar molecules due to their net dipole moments. Finally, if we look at an example of a molecule that contains multiple bond moments, but overall there is no molecular dipole moment. And that example is our carbon tetrachloride. So you can see that carbon tetrachloride, or tetrachloromethane, it has 4 bond moments associated with each of the carbon-chlorine bonds. Okay, so each of these bonds are polarized due to the differences in electronegativity between carbon and the chlorine molecules. But what's important to recognize is that because each of these bond moments are in equal and opposite directions, the net dipole moment for this molecule is 0. So carbon tetrachloride is considered to be a nonpolar molecule because there is no molecular dipole moment. We have individual bond moments associated with the carbon and chlorines, but overall, they will cancel one another out. By recognizing that molecules have a net polarity, we can categorize molecules based on their polarity. So with respect to solvents or various organic compounds, molecules that have a net dipole moment that is quite large are considered polar. For example, water is considered a polar solvent, methanol and ethanol, the alcohols, acetone, and chlorinated solvents like chloromethane. Whereas if we're wanting to work in an environment that contains a nonpolar medium, we may wish to choose a solvent like pentane or hexane or carbon tetrachloride. And of course, there's going to be solvents that fall somewhere in between, such as the ethers and dichloromethanes. These solvents have some polarity associated with them, more so than pentane and the hexane, but less so when you compare it to water and the alcohols. So by recognizing that there are differences in electronegativity between elements, we can identify where polar covalent bonds are found in molecules, and by looking at, in general, the number of polar covalent bonds found within that molecule, we can assign molecular polarities to those systems as well. And that's going to allow us, again, to identify regions where we expect reactivity to occur, as well as allow us to assign properties like polarity to these molecular systems. So if you have any questions on electronegativity and bond polarity, or dipole moments and molecular polarity, send me an email or start a discussion in our forum. Thank you.